Yeah, I mean, a lot of what I'm going to do today is stuff I do with various schools' audiences. I tend to do sixth form mainly, but some GCSE. So this is one that Mike Pearson and Rich wrote, which is just supposed to illustrate random, a bit like coin flips, really. You know, each is likely, there's 20 forks, and each one is a 50-50 chance of being left or right. So it's a bit like flipping a coin 20 times, and if it turns up heads, it goes that way, tails goes this way. So this is, you know, the chance of landing here is chance of getting no heads in 20 flips, the chance of landing there, getting the chance of 20 heads in 20 flips, which is a half times a half times a half times a half, it's about 1 in a million. So this is supposed to illustrate a 1 in a million chance. I get a whole talk about 1 in a million chance. But meanwhile, you're getting this binomial distribution being built up, because this is, you know, how many flips, how many heads you'd expect. And it's looking rather nice. But each one is completely unpredictable. But, you know, once we've got 500, they end up forming this nice shape. But then we can sort of move the little man in, of course, if we want to live a life of risk. So the lesson is never stand under a tree in a thunderstorm. never stand in the middle of a binomial distribution in a thunderstorm. He's going to get whacked again and again and again because he stands there. So that's you know, basically just a filler when people are coming into the class. But it's quite useful. And all this is downloadable from our website, Understanding Uncertainty. Okay, great. Where are we? What am I talking about? Where am I? What planet am I on? Right, okay. So I'm going to talk about why do people find probability and statistics unintuitive and difficult. So that's what I deal with all the time, public understanding stuff. I'm also going to feature quite a lot of what I call naughty numbers in the news, because what I do to try to sort of engage people is look at current stories, stuff in the newspapers, and it's almost guaranteed that every week you can find some howler that you can, it's usually the headlines. Our website is Understanding Uncertainty. I'm funded by Winton Capital Management, a hedge fund actually pays for our work, which is nice of them. They've got enough money to give some of it away. So I do stuff with a blog, I've got various articles. I'm on YouTube. We do this Risk and Probability Roadshow with MNP, goes out to schools. I've just done this TV program. Skydive.
Smart and witty.
Sorry?
Smart and witty.
Smart and witty. Yeah, well, I don't know who that is. I know it's smart. I did not write the blurb. Smart and witty. Not very smart. But the thing that most impresses the school audiences is the fact that I was on Winter Whiteout. And so I'm not going to show you, but I show clips of me doing the red balls and falling in the mud. And that goes down really well. So this is my promotion of risk-taking, the fact that I did it. I didn't do too badly. I was 7th out of 20 in the heat, and I didn't actually break anything. But so this is up to my credibility. And I can't resist the plug. I've got a popular book coming out, so I'm sorry, this is pure marketing. Okay, enough of that. Maths education is important. You've probably seen this one. I got it off Twitter, but I thought this was a really nice example. why we need math. And what I'm timing you, of course, is timing the laugh, which is what I do with the schools audience as well. How long until they get the bad joke. This is another one. Probability. People find ratios, proportions difficult. So a 1/3 chance of being killed. 1/3 of bikers are killed on Kent roads. You think, hang on, and motorcyclists made up 35% of people killed or seriously injured. So we got the denominator wrong. It's 35. It's not 35% of bikers. It's 35% of accidents of bikers. Really easy when you talk about chances to get the denominator and get the reference class wrong, get the sample space wrong. We're talking about accidents. It's the denominator, not bikers. Hey, that was last week, and the next day, it's a shame. Somebody told them. It's really, people shouldn't tell them when there's things like that, because they replaced it. But it got grabbed by somebody and put on Twitter before they took it down. So it'll be there forever now. Used relentlessly. But it's a really important thing. The headline writer, it's obvious. It's very easy to actually make this kind of mistake, to get the denominator wrong when you talk about chances and so on. So I'll talk about some of that. So basically, my conclusion, I've been 40 years in the trade, academic statistician and everything, and after all these years of research, I've decided that the answer to that question is because they really are unintuitive and difficult. I think probability stats is difficult. Any probability question, I read the newspaper or something like that, I say, hang on, stop, I have to sit down, concern aloud for a bit, and read it, think, do it 2 different ways, and then I say, well, obviously the answer is. The really tricky, the simplest probability question, I read it and I think, I can't answer that, it's so tricky. So I think it really is difficult. And why I think it's difficult, in fact, is that I think that probability is as difficult a concept as complex numbers. They are both virtual quantities. Complex numbers are square root of -1. It's not there, you can't measure, you can't see it, it doesn't exist. You have to just sort of imagine that it's there, it's an imaginary number. Probability is an imaginary number. You can't measure it, you can't see it, you can't weigh it. You know, where is it? Where is probability there? You can't see it. It's a completely imaginary construct. It's really difficult. I think it's very reasonable that people have a lot of difficulty with it because nobody, it was just, I think it's been invented, I don't think it exists. And it wasn't invented until the 17th century, just a few years ago. Other things were going on for ages. Probably it's only been invented for a few years. So averages. Here's a nice one. Child obesity forecasts excessive so report. A separate opinion poll yesterday suggests that 50% of obese people earn less than the national average. Yeah, quite quick. Schools don't take, it's only if they've studied medians and things like that they can get this, quite quickly. Because, 50% of everybody earns less than the national average. Because you use median average for income. And you think, God, that's so stupid. I love this, particularly disturbing reading. So, I love this stuff, but you think nobody could be as stupid as that. But it happens in more subtle ways. Last week, Leeds Infirmary Inquiry, which I've been involved in, which is called Thames College, you're doing stats now, which is quite fun. The person for the central cardiac, the president of the Association for Cardiac Surgeons said, not aware of any centres having a higher than expected mortality. And in this case, expected means average. So no centres have a higher than average mortality. But hang on, no, half of all centres got higher than average mortality. That's what an average is. And it's correct him. It's a completely idiotic thing to say. He means sort of significantly. Half % hospitals roughly higher than average. So this stuff crops up all the time. Sort of idiocies. Surveys. Oh, did you see this one? This is a cracker. Again, I got it off Twitter. This is the Church of England, just last few weeks ago, 26th of March. 4 out of 5 believe in the power of prayer. Well, that's a good statistic. And then right down the bottom, this is the Church of England website, right down the bottom, it actually says the question that people were asked. And the question they asked was, irrespective of whether you currently pray or not, if you were to pray for something at the moment, what would it be for? And anybody who even dreamt of answering that question counted as believing in the power of prayer. So it's only people who refuse to answer who counted as non-believers. So it's extraordinary. So naughty Church of England. The Daily Telegraph, went with it. 6 out of 7 people believe that prayers can be answered. So there's a real naughty number in the news, and they crop it all the time. And that's quite subtle. It's good to see what's the number, what's actually being asked. Okay. So what's probably mean? And you think, well, people teach in poverty scales, words, use equally likely events and everything. I'd say it's a really tricky concept. It's not directly measurable. Probably does not exist. It's quite a respectable intellectual position, which I hold. It's a bit minority in the trade of statisticians, but I hold it very strongly. Someone's written a 2-volume book called Theory of Probability, and the first line is probability does not exist. He says it's just like a fairy tale. It's just like fairies. You can't see it. Just people just made it up. So what that takes me for is any description is a metaphor. It's very liberating. It means that we don't have to say probably instantly. We have to use metaphors. Like, and a metaphor would be, of 100 people, how many would you expect this to happen to? Or if I kept on doing this, what would be the long run frequency? Or just what would be my reasonable betting max? These are all metaphors. So the point that I work in risk communication, doctors and people in weather and all that kind of stuff. Flooding, how should flood risk maps? They use 1 in 100 and things like that. They use, actually, the worst thing is 1 in 100 years to describe floods. well, I'll argue it's a terrible way to communicate risk. So people are very interested in different metaphors, how you might say things. So this is something we do with doctors. They want to tell someone that 20% of their cases with their condition would suffer certain bad outcome in 10 years. You have to tell this person, what would you use? You could say 20% chance. You could say 0.2 probability, but nobody would ever say that. But you could say 20% probability. You could say 1 in 5 chance, that odds language to use it. 20 out of 100 cases like you, 2 out of 10 cases like you, or none of the above, or use numbers, or depends on the person. So these are all different ways, and from a mathematics point of view, you think, well, they're all the same. They're not all the same. These different phrases carry very different meaning for them. And some of them make it much easier to make comparisons and do judgments than others. And essentially, what I'm going to argue is that all the recent psychological research suggests that that is the phrasing that makes it easier to do probability calculations and understand stuff. This is terrible. These are terrible, pretty bad. Doctors will tend to only use those two, and this is now the favourite among doctors to use. So I'm going to be, that's why the point of the talk is to argue that, and then show some teaching materials we've been preparing based on this kind of concept, the idea of expectation in a group of people, trying to keep away from 0.2 and 20%. So the point, this is a big area of research we're working on. People are writing long papers, doing surveys of statistical numeracy for health. So this is sort of adult education, where people should be able to do these sums, to know what they're saying. And this is a typical question. Which of the following numbers represents the biggest risk of getting the disease? 1 in 100, 1 in 100, 1 in 10. This is on adults, telephone survey. How many people do you think get that wrong? Which is the biggest risk? So I'm not going to test you. How many do you think get it wrong? 75%. We'll get it wrong. It's not quite that bad. They're very cool to get it wrong. So, and that's quite reproducible. It's because this odds language is tend to be confusing people, because the biggest number is associated with the smallest risk. You're changing the denominator to keep the numerator fixed, but not changing the denominator. And I find, I don't know what lives in I live in a flood zone. I got a flood risk map that says that my risk is less than 1 in 75 and more than 1 in 200. Now, I find that a really, really difficult thing to understand. I see it written down. I say, I'm a professor of risk. I can't understand that. How does everybody else? It's less than, and that's how it describes it. I live in the place, less than 1 in 75. And then they start talking about 200-year return periods. So hang on, it's less than it returning every 1 in 75 years, but more than I cannot understand that. Probably going to ditch that language, to change into denominator, and moving to a language where the biggest number is associated with the biggest rates. I'm using percentages. Now, so numerator is denominator, but it turns out that actually just what denominator you choose can make a difference. So here's an experiment. I'm not going to test you on, but this has been tested on a very common experiment to do on essentially non-numerate people. So which would you prefer? You're going to get a prize if you pick a red bean. Could have done it, should have done it back there. This one's got 9 white beans and 1 red one. It's got 92 white and 8 red. Which bulb would you rather choose from? To give you all the information, which one would you rather choose from if you're going to win a prize to choose a red? Now, we're all, exactly. So, who's going to choose that one? Well, yeah, you're all rational, sensible people who do the sums, but in fact, the general population, very reproducible finding is that, in this case, the majority of people choose right. A substantial minority choose the right idea because there's more chances of winning. The numerators, it's called ratio bias. So a risk of 10 out of 100 is bigger than 1 out of 10. People take more notice of the numerator than the denominator in the numerators. So the argument for that is that that's ratio bias. Denominator neglects, but you take no notice of the denominator at all. And we think, oh, how could anyone do that? Well, every time you read a newspaper, you see that. Because people say, oh, a child has been, knocked over at school, therefore this is a really risky thing. Something bad has happened, therefore there's a very high risk. This is really risky, big story. Actually, there's no report of the millions of children who went to school, without being there. We don't read a newspaper that says 3 million children go to school, no kid. I would read a newspaper like It's really dull. But people like numerators, they look at what happens, not what didn't happen. And this is very difficult to get over. So the way people recommend doing the communication is to have a fixed denominator. Out of 1,000 people, what count? So then we're going to got this idea of relative risk. They who are in this area with greater than average risk of shock. Average, not compared with Cambridge. What's average? So this is, and this is to do with increase, percentage increase. People are bad at percentage. Isn't that lovely? Yeah, a bit slow there. Come on, speak of things. Yeah, isn't that wonderful? It's just a great answer. Yeah. So people find percentage increase quite difficult, and you can see why. Because and yet in a way we should be able to do this kind of stuff, but we're not trained to do it, and it's difficult. So we're told these changes all the time. So you know, this is a direct-to-consumer advertising of a statin, which isn't allowed in this country, it is in America. Reduce your heart attack risk by 36%. Whoa, big font, pretty impressive. Okay. Now, what does that mean in terms of absolute percentages? Well, in tiny print down here, it says that it means that your risk is reduced from 3% to 2%. That's the 1/3 reduction. So actually, 100 people, the logic is 100 people are going to have to take these tablets every day for 5 years to prevent one heart attack stroke. Now that sounds a bit different, but you know, that 1/3 sounds really good, like the 200% increase in goodness. So, it's actually, you know, this has been discussed a lot in the pharmaceutical industry, but now in the UK banned the use of relative risks alone. Yeah, they say the pharmaceutical industry must give absolute risks. Relative risks are known to mislead people. And you can see it in the news all the time. This is a recent WHO report from Fukushima, about Fukushima. New York Times says there's a very low health risk in Fukushima. Amazing. Wall Street Journal says a tiny cancer risk after things. I mean, you know, very rare for a newspaper to play something like this down. So tiny cancer risk on an absolute scale is a very, almost non-measurable. It will be actually non-measurable. In fact, it will not be measurable. It's kind of theoretical increase in risk. But the Guardian just couldn't resist. They just couldn't resist finding the biggest percentage change in the whole document and pushing that onto that. 70% higher for people. So the cancer risk, oh no, hang on, it is only thyroid cancer, which is extremely rare. So an extremely rare thing might become slightly less extremely rare in one group of people. Okay. That's what the story is, but no, so the Guardian just couldn't resist it. Yeah, so this is the kind of stuff I love. It's just so dreadful. This is the daily bacon sandwich. Raises the chance of pancreatic cancer by almost 1/5. Okay, how are we supposed to do that story? I would love it that kids could see that and take it apart. And it's actually, but it's very difficult, because to know what that means in terms of absolute risk and what it actually means for us, we have to know what the risk of getting pancreatic cancer is in the first place. We have to know the baseline, because it's just a change. You have to know what the 20% of. And it turns out that, although they don't tell you, you have to search around for it, it's a 1 in 80 chance of getting pancreatic cancer during life. Horrible, not horrible cancer, very nasty indeed. But so what we're saying is we've now got to do a 20% increase over 1 in 80. You know, it's a mixed metaphor. I mean, that's a very difficult thing to do. Difficult in your head, you know, to do it in the head, 20% increase on 1 in 80. Not at all easy. So the way to make it transparent is to choose a suitable number. Now, this business of choosing the suitable denominator is quite tricky. I think with any exercise is always have to be given. But let's say 400 people not eating a bacon sandwich each day. So that of those, 5 will get pancreatic cancer during their lifetime. That's the 1 in 80. Now let's compare the 400 people who stuff their gob with that every morning of their lives. Can you imagine it? You feel a bit sick. Now 20% has a 20% extra risk. So there it is. That's the 20% extra risk. Did you see it? That is the 20% extra risk. 1 extra risk. So now, through this mechanism, we've shown that all these people would have to eat that every day of their lives for this 1 extra case of pancreatic. And if you believe it anyway. So that makes it not such an exciting story. Now, to actually go through that, journalists are incapable of going through that reasoning. it's difficult to do unless you use a transparent representation. And I think and what psychologists have said in the same for some time, we would like to see this getting more into the teaching community. The most transparent representation is to have a number of people, a large number of people, 100, 200 people, then what would you expect to happen? So it's based on expectation, whole numbers, it's called a natural frequency approach. So don't use probability, don't use odds models. Try to tell you what would you expect to happen. Now, one place where that's actually being used is this on breast cancer screening. I'm on the group of people who are redesigning the leaflets for breast cancer screening. And breast cancer screening has become extremely controversial in the medical profession. A really polarized community. Some people are very pro it, some people are very anti it. And so they got people to do a review. The people they got to do the review knew nothing about breast cancer screening. The main qualification to be on the review team is that they've never worked in breast cancer screening. And so they reviewed the evidence and they came up with some data, some numbers that are going into the new leaflets. But the new leaflets will be based on this principle of shared care and informed choice. They'll present pros and cons, and they won't make a recommendation. This is an absolute first, controversial, that the leaflet about breast screening will not recommend breast screening. It's not going to be a sales pitch. It's going to be a balance, which is an innovation in all types of risk communication. We're trusting the public to be able to make up their own mind. And that means having transparent representations. So I was presented information to a citizens' jury of women and we looked at all different representations. And it's quite clear that the representation of what you would expect to happen to 200 people was easily the winner in terms of people's understanding of what happened. And so we tried out various graphics. Now, I don't know what you think of these. In fact, I think they're not, in the consumer testing of the leaflet, people found them difficult, and so I think in the end, the graphics aren't going to go in. It's a real shame. This is the kind of thing we played with. Saying 200 women, what you'd expect to happen who go for screening, and 200 women who don't go for screening. And the same number are going to get breast cancer, because screening doesn't prevent breast cancer. This is a frequency tree. It's like a probability tree, but with frequencies. So it's a probability tree with a frequency tree. 15 will get breast cancer anyway. If you go for screening, 12 will be treated as 5. Sadly, 3 will die early because of their breast cancer, even though they were screened. But if you don't go for screening, 4 will die early from breast cancer. So 1 death, early death, is prevented out of 200 for screening. 8 are treated as 5. What happened to the other 3? The other 3 will never know that they've got breast cancer. They'll go through their life, they'll die of something else, and the breast cancer will never have affected them, subclinical. Whereas those 3 women in this group are treated for breast cancer. That was actually unnecessary. That's the trade-off. 3 or treatment, 1 treatment, 3 treatments. So the trade-off is that there's 3 times as big a risk of being over-treated than there is of having your last. Now, we don't know what the effect of this information will be. But the crucial thing is it's the first time that anything's been presented as hopefully as transparent as this. A lot of people don't want to know, they want to ask this. These numbers are slightly at the back of the leaflet, etc., etc. This is another representation using icon arrays. This is 200 women going for screening, 200 women without screening, and this shows the same image, that you've got 1 extra dying without screening and 3 extra being treated in the screening. That's the trade. So these representations are seen as the best way to try and communicate. They're actually very complicated risks. The graphics, they say icon arrays are very useful graphics. They show you really well. There's a good graphic. What about that one? Pie chart? Yeah. Now this is nice. You can do this with really young kids. What's that? That's not a proper pie chart. It is for Fox News. For Fox News, that's a great pie chart. I think that's just stupidity. But sometimes it's mendacious. Look at this one. Oh, look, this is a standard one. Bush tax cuts expire, now 35%. And that could be 39%. So, judicious choice of axis. This is a really nasty one, because unemployment rate under President Obama. So 9%, 8.9, 8.6%. Hang on. Look at where that final data point is. It's actually above 8.8%. So they just fiddled the graph to make sure it didn't go down. So otherwise it wouldn't look like that. It wouldn't look great at all. So that's, that is just really criminal. Again, Fox News, you whole talk on Fox News. So other people use graphics to communicate uncertainty. The Bank of England, for example, I think this is quite a nice example of forecasting, where these represent, this is a 90% interval, the outside bit of the fan, and the slightly more shaded was 80%, 70%, 60%, etc. So they're stating they don't know, and they use this metaphor of 100 situations like this. 90 of them we expect to be in this band. The other 10 we don't know where they'll be. They don't even know what happened in the past, which is quite interesting. We don't know what's going to happen, and we don't know what did happen. And we certainly don't know what's happening at the moment. So this is what's called being upfront about uncertainty. And people don't like it. Journalists hate it because they don't even put in the best estimate. So nobody can say the Bank of England got their projection wrong, so they don't give a projection. But like this was back in 2007, this was their fan. And they, 100 occasions like this, that's what actually happened. Here's some. They're completely unapologetic, because there is a warning, 5% is down here, and it's unassigned, could be anywhere. 1 in 20 chance will be off the map. So they don't make it very clear, the graphic is not clear enough for that. So, there's an example. The other thing, I look for anywhere where people are communicating uncertainty. Hurricane forecasting, we don't have hurricanes, we've got hurricane forecasting. This is known as the cone of uncertainty. Cone of uncertainty. And they say they give you a central projection and a 2-to-1 chance from there and there, based on computer model. So that's what they do in Florida. What they found is that anybody who lived there thought, oh, we're okay, and didn't do anything, and complained when their home got flat. So they ditched now the central line, the black line. They followed the Bank of England and not put in central projection, because everyone gets obsessed with this black line. No black line, just the curve. But that's interesting. What do you think of that compared with this, which is an alternative graphic used on the national news? Obviously, you preferred this one, which is based on similar computer models, but they put on the actual paths, called possible paths. So now they're using a different metaphor of possible futures. We don't know what's going to happen. This might happen, that might happen. Here's a list of possible futures. So again, it's a metaphor for uncertainty. And one I really like. I love this possible futures. How things might turn out. Out of 100 ways things might turn out, how many will there be this time? Again, it's a metaphor. Maybe everything's predetermined, fate, who knows? It doesn't matter. We don't know. So, and this is done in weather forecasting all the time. For example, the huge storms in 2007, 5 days beforehand, the Met Office made multiple forecasts. 25 forecasts there, they didn't know, they thought they were roughly equally likely. In this one, nothing particular was going to happen at all. In others, it's going to be an enormous chunk of pressure, gradients, things like that. I don't know what actually happened, it must have been something horrible at the East Coast. So, maybe it was horrible at the East Coast, maybe that, something like that. But one of them they didn't know. And so that's how they give probabilities for future events. Talk about possible ways things might turn out. Very powerful metaphor. So I like this in medicine, in communicate risk. So all the possible ways things might turn out. So, when I went to my GPs, and he told me I got a 12% chance of a heart attack or stroke, statins could reduce it by 33%. Okay, so then I have to do the maths. Again, interesting challenge. What does that mean? It's an interesting question to say. Okay, my risk is 12%. People like me, my risk is 12%. Statins could reduce that. That's an absolute risk. That's percentage points. This is percentage change. How many people like me would have to take a statin for 10 years to avoid 1 heart attack? That's not an easy thing to do. Not easy at all, unless you translate it to 100 people like me. So here's 100 people like me. That's yellow, isn't it? Here's 12 of them who are going to have a heart attack or stroke if they don't take their statin. But if they're good boys, they all take their statin every day. That's going to go down by a third. So 4 of them will have that heart attack or stroke prevented. So that means that 20 25, on average, 25 people like me have to take the tablets every day for 10 years to prevent one heart attack. And that moving through that reason is very difficult unless you use an appropriate representation. Using representations like this, it can actually become, people can answer this stuff. You can show it again and again. You can answer these difficult questions if it's to use the right representation. I quite like the possible, this is 100 people like me, because there aren't 100 people like me. So I like to think of 100 ways things might turn out for me. So here's me, 100 ways in the future. Which one's going to happen? Wow, take your pick. And then you can scatter them around to make them really round. So my future is like throwing a dart at here. I'm wondering which one it's going to hit. So I think this is a great representation of just facing up to uncertainty. So I shouldn't go on. I started a bit late, so yeah. I'll whip through this very quickly, because what I just want to describe, I want to just plug our teaching materials, just put up on English, that use these ideas which are being developed in psychology about communication. And so we say that we should, when teaching probability in class, should start with a problem, and do physical experimentation when possible, and think of narratives, think of stories of how things develop. You do this and then you do that. And then represent them in different ways. 2x2 tables, frequency trees, and Venn diagrams. I'm not that keen on Venn diagrams. All I love is frequency trees. So I always think of frequency trees as encompassing, like there's breast cancer one, there's 200 stories, there's 200 women's lives you were drawing. Which, and similarly in the class, you do 200 experiments, you summarize the class experiment as a frequency tree of what happened at these stages. Very powerful. And then essentially we say, we can spot patterns, we've got animations. We can ask questions about expectation in future experiments. So if we did this another 60 times, how many times would we expect this to happen? Through symmetries and arguments like that. And finally, at the very end, we can change our intuitive fractions and we get to probability at the very end. Probability arises, it isn't at the top, it arises naturally as really an expression of expectation in a single case. And there's quite, again, a respectable theory that says that expectation is more fundamental than probability. Probability should best be thought of just as expectation in a single case. The problem comes at the end. Throughout, we think in terms of 100 people, of 100 cases, how many would you expect to happen? So that's our idea. We've got great expectation, we called it, and Jenny Gage with a whole lot of nice material. We've got examples and animations and things like that. And I'll just whip through an example very quickly. I'm sorry to be too quick, but basically, this is very suitable for probability trees involving a sequence of events. So we're talking about dependent events as well. So we're trying to teach conditional probability, usually two events. You do something and then something else happens. And the chance of the next thing happening depends on the first. But the idea is that we are trying to embed in this sort of standard data cycle of doing investigation, collecting data, processing, do that. Although I personally believe in trying to keep the teaching of stats and probability separate. Of course, you use statistics to look at your probability questions, but I think that I prefer just thinking of this as probability rather than stats and some stuff. So this is one of our ones we've got. Dog ate my homework. And this is the teacher, is the LI detector, who claims he can tell when students are lying about their homework. And it's true, if they are lying, he always can spot it. Unfortunately, he's a bit heavy-handed, and he sometimes accuses some students of telling the truth. Dog really did at the homework, and yet the students accused him of lying. So I'm sure we get people like this. So what are the chances? So actually this last statement is deliberately ambiguous, and one part of the exercise is to try to work out the different meanings of that. So what we do is first we'll do some experimentation. We've got some special dice, and we've got some cubes. This is starting from Germany. They did a whole lot of work with primary school children, teaching conditional probability with cubes, and essentially Lego type cubes put together. And found it to be very effective, so we've been copying it, in which you throw a dice, and if you tell, so every student first of all can see whether they're a liar or telling the truth. And if they get a 6, they're lying. So 1 in 6 of students, on average, will be lying. The rest are telling the truth. And then they get a little red cube if you're lying, blue if you're telling the truth. Now, if you're lying, he definitely spots you. So he gets accused, and it's a yellow cube if he gets accused. So this is a two-variable event. He's lying and he's accused. If you're telling the truth, you throw another dice. Now if he gets a 1, there's a 1 in 6 chance he's going to be unfairly accused. he gets a yellow, blue and yellow. So that's a sort of unfairness. And otherwise, he's telling the truth and the teacher accepts it. So you've got these four combinations. And what you do is then get students to do, say, 36 at a time, and then they collect the information together, and they represent it in different ways. So there's all of it that happened in the experiment. And they can represent it in different ways. This is a 2x2 table representation, which is very nice. Or they can represent them as probability trees. And one of the things that we want to really go is this multiple representations of the same information. Because sometimes one is better, sometimes the other better, and you really should be able to move between these representations. So nobody's up in the top corner, and we could make it so they were, did align that. So that he did miss some of the lines. That's not even good. And then you can ask various questions. You know, of the ones telling the truth, how many are accused? And of the ones accused, how many are telling the truth? And that, then this way, of course, is very usually things that are very difficult to answer. But in this representation, it becomes completely trivial. You know, if you are accused, what's the chance of telling the truth? Which is 5 11. I can't do it. 5 11, so I can't run. I can't do it. You know, these questions, you just can't do them quickly. So, and we got this. Just to give you a link, we've got animations that you can do, which do I get my homework, and you can hand in the homework and it decides whether you're telling the truth. Are you going to get accused? No. That's fine. And then are you lying? Are you telling the truth? Are you going to get accused? No. And then you can do a whole lot more, and it produces a 2x2 table for you. But I mean, this is, in a way, this is cheating. It's only if you really want to do a lot. If you really want to get the students doing this, constructing the tallies and doing the 2x2 and producing the frequency trees themselves. So we can stop and put that over. There's misery. Go away. Stop. How can I stop? Stop. Right. Cool. But then you can represent, I love frequency trees. You know, this says out of 36 things, what happened? 7, you know, lied, and 29 didn't, of those, and then accused, and you immediately see the properties out of these numbers out to 1 exception. And then, this is the crucial next step. You say, well, if we did it another 36 times, how many would you expect to happen? What would you expect to happen in 36 new cases? And this, in a way, is the big step. To say, okay, out of 36, we would expect 6 to be lying, and of those that will be caught, we expect 30 to be telling the truth, and of those, 1/6 we expect to be accused of. So it turns out that of those accused, there'd be 11, and 6 would actually be lying. So it's 5/11 chance that somebody accused is actually telling the truth. We wouldn't get to that. I mean, essentially it's an A-level question. But it's an A-level Bayes theorem, it's Bayes theorem, which is A-level, but we put that in just as key stage for somebody wants to go at it. But still it's expected frequency. And then the final stage, we can then divide 6 by 36 and 6 by 6 and put probabilities on the branches, and you get probabilities. And the crucial thing is from that, and I won't get into detail, but we do show how you derive the multiplication rule down the tree by using these frequencies. So the multiplication and the addition rule falls out naturally for the frequency, rather than sort of being imposed. I was looking at some material yesterday, and the multiplication rule is just it's just there. It just says that's it, you multiply down the tree. But you do multiply, it's a very good rule to remember, you multiply down branches and down across branches. But there's no reason why you should, whereas in fact it's very simple, it's just a proportion of a proportion. It's what we're doing with the 400 people eating their bacon sandwich. So you derive the multiplication as a proportion of the proportion. So yeah, that's it. So conclusions, probability is tricky. Okay to think about it thoroughly. And recent psychology research, people can really help to solve these difficult problems using frequency, narrative, multiple representations. And so a person can expectations with astronomy, expectation comes from the A level, but expectation should be common, preferably to GCSE. And this could be important in teaching some problem solving. Maths, for example, post-16 qualification, those sorts of more practical problem solving maths. This is a really valuable technique for solving really quite tricky problems. And yeah, it's not that. Thanks very much.